Okay, so our next speaker, it's actually, I think it's a tag team affair. We have Naima Ghaffarian, I hope I've got that correct, and Milad Khaki will both be presenting. And they're coming from, well, first of all, their talk will be about AI methods are solving complex beamforming antenna and radio systems. So sort of an AI product application, I think, is one way to look at this device development application. And Milad in particular is a postdoc working on cognitive neurophysiology and developing brain lab. He's working in that laboratory. He's looking at optimization of practical research problems using constraint programming and a rather diverse set of techniques adopted from both AI and machine learning. And a lot of applications, interestingly. He's looking at satellite phased array antenna optimization, big data analysis of smart water meter data, and currently he's looking at some interesting problems working at memory and 3D representation in rhesus macaque monkeys and applications of AI and epilepsy. So I can't imagine a more diverse set of applications. I think that sounds very, very interesting. Okay, so I would like you folks to go ahead and share your screen, please, and feel free to dive in.
Sure. Thank you for that nice introduction. Yeah, I've always been interested in any kind of application that I can use artificial intelligence, and there are lots of fields, and they're ever expanding. So any field that I can apply artificial intelligence, I would play around with them. So the work that we've been doing in CR's group, we've been working on intelligent antenna systems, and which are obviously powered by AI. There are lots of parts of the system that are improved, enhanced, or revolutionized by AI, actually. So the content of our talk is going to be, just to make sure you can hear me clearly. There's no problem?
Yes, we can hear you. Yes,
awesome.
It's good.
Perfect. So the application, first of all, I'll talk about the application of phased array antennas. What are phased array antennas, and why there have been we are hearing more and more from them in the mobile satellite communications. And then I'll talk about the application of artificial intelligence in the satellite tracking and beamforming and stuff like that. And then Naima will talk about her part in application of applying machine learning for designing complex antenna structures. So let's dive in. Mobile satellite communication has been around for a very, very long time. We have satellites that are orbiting around the Earth, and we have receivers and transmitters on the ground level, and we have communications with them. So these communications have been improving over time. We have different satellites that are which are on different levels that are orbiting around the Earth. We have geo satellites, which are orbiting with the same speed that the Earth rotates. So it's basically, they're fixed in the location of the sky. That's why we don't see some of the dishes are fixed. Also, we have LEO satellites, the Starlink system that has started with powered by Elon Musk, is a new application of LEO satellites. They're much faster, and they're closer to Earth, roughly at the same level that the International Space Station is. So they can rotate around the Earth much faster, around each 90 minutes they can rotate once around the Earth. So it's much harder to focus on those satellites and keep a antenna focused on that and targeting them. So that's why we need more powerful antennas and much better technology to focus on those. Sometimes you need 2 or 3 reflected antennas like these ones if you have a moving substrate, a vehicle, to basically track those LEO satellites. They are also heavy, bulky, prone to failures, and suffer from complex feeding systems. On the other hand, we have these phased array antennas which are flat. They're low profile and they're fast. And the beam scanning, which was done, so basically focusing on the satellite, which was done previously mechanically, is done partly previously during the past few decades. They were partly done mechanically and partly electronically. And right now, all of them are electronic. So you have a satellite that is mounted on a top of a train, and it basically has the satellite communication. It can focus on different satellites around the Earth without having any actual mechanically moving parts. So we have this scanning of the space, sky, and we can focus on different satellites without any moving parts. So in order to achieve that, we have an element called phase shifter. That's basically by shifting the phase of the receiving signal and combining those signals together, we can have we can focus basically on different satellites. As you can see here, it's possible to sweep the entire sky without any problem. So this process that you can focus on different satellites or tune on a specific satellite is called beam steering, and it's the process is involved with finding the direction of the satellite using the receiver antenna. We need lower accuracy for the receiver antenna, and then once we found the satellite, then we can tune on that, we can focus on that, and then we can send the signal using the transmitter and basically have our bidirectional communication, full duplex communication without any problem. So this is one of the products that we had 10 years ago. It was developed 10 years ago. It was the only receiving camera. It's as you can see, even at that time, it was low profile, and now it's much smaller. You can fit one of the modules on the palm of your hand, and then you can put all of them together, a bunch of these modules together, and have a very powerful antenna with relatively low cost, which is dropping day by day. So yeah, and you can basically have communications in airplanes, trains, and any moving substrate is possible to do it. So let me talk about the application of the phased array antennas in the mobile communication. In the previous generations of mobiles, third generation, fourth generation LTE, we had we were using lower frequencies. I'll get to AI part soon enough. The next slide is going to be AI. It's just a brief, small background about these things, and then I'll jump into AI. In the previous generations, we had lower frequencies, and the signal can be dissipated all over the place. And you have your cell phone. You don't need to see actually, or your cell phone doesn't need to see actually the transmitted tower. And in that way, the communication is possible, but the speed is limited. In the fifth generation and sixth generation coming after that, you need to, in order to increase the speed, you can have up to 10 megabytes per second download, and it's going up 100 megabytes, and every day it's going to increase. In order to have that speed, the antenna on your cell phone needs to see the transmitter antenna of the tower. And in order to achieve that, you need to either you have to tune this tower to see your cell phone and tune your cell phone to see that and just keep them stationary, or you need a satellite antenna that is quite fast and can trace different clients with high accuracy and in a fraction of a second. and that's when the phased array antennas are coming into the picture. And this is actually the future of all of the satellite communications. So how do we do? We talked about this targeting of the antennas and targeting of the satellite and focusing on different satellites. How do we do that? I said that we have the focus on the received signal from the satellite, and then we improve the power and then send the signals, and wave my hand around a lot. But now we'll go a bit more into the details. As you can see here, we have this small red dot here. This is the location of the satellite, which I'm showing on this green dome. And these are the receptions that we are seeing. We don't know where the satellite is. We, based on the receiving signal, we will improve our orientation and improve the direction that we see the signal from, and then improve it further and basically make sure that we are actually looking at the correct satellite. And that is done using a lot of artificial intelligence. So as you can see here, we have 10, 20 readings of the received power, and these are the blue dots that you see here. And based on these received power, then we can predict where the satellite is, and then focus on that point and make sure that we get correct and high-powered signal. Excuse me. So this is a block diagram of the phased array and systems. We have the satellite tracker, which basically tries to, it basically does this tracking here, generates different orientations, and the system has to follow them. We have the phased array system, the hardware that basically does the actual job that the satellite tracker algorithm tells it to. And we have the power detector that basically receives the power from the signal that we receive from the satellite, and then this power goes to different parts of the system. We'll record it for historical predictions, and then it goes back to the tracker algorithm as well. So in a complicated system such as phased array antenna, feedback is quite important. The power detector feedback is quite important. Recent historical data is quite important. I might get noise in the receiving signal, and based on the other received signals during the past 10 seconds, for example, I can be sure that I'm not making a mistake based on one erroneous reading. And also the current location. The current location, I know where I'm at. Right now, if I go through a tunnel, when I come out of the tunnel, I'm looking at the vicinity of that specific location in the sky. I'm not going to confuse myself. So these are the information that we'll use to input into the AI system and basically improve our accuracy and performance. There are three main points that we use artificial intelligence in the satellite tracker algorithm, and one in the size of the steps that we, basically the steps that we have here, the difference that we have here is also determined by AI. I don't think that I'll get a chance to talk about this part, but I'll talk about these two. So digital phase shifter element. I talked about the digital phase shifter element. What is this element? It's a digital attenuator which is combined with a phase shifter. So basically provides a delay in the signal and then change the amplitude of the signal. It's an ideal phase shifter. In reality, phase shifter and attenuator are not independent of each other. If I change the amplitude of the signal, the delay will be changed, and vice versa. So their behavior is a function of several environmental parameters, which I don't want to bother you. Also, there's quantization error, lots of different types of errors that are available in digital systems. For example, at the end, the phase shifter, digital phase shifter that we are expecting to be a perfect system has plus minus 30 degrees of error in the delay and 3 dBs in accuracy in the amplitude changes. So all in all, we can say a digital system does not mean that it's ideal. Sometimes it's far from ideal, which is this case. And there are all other digital systems. We have to know how to deal with these problems and how to take advantage of the capacity of the system. However, a good thing about digital system comparing to analog systems, their predecessors, is that most of the time we can actually predict what this digital system is going to do. It's not ideal, but we can predict how it's going to react and what are the errors that we are going to expect. That's a good thing about digital systems. So in this case, that we want to basically find the location, actual location of the satellite, we need to tell the system to go to a specific phase and use a specific phase and amplitude. And and we know how the system works. So we trained an artificial neural network to basically do this job for us. We tell the system the correct attenuation and phase shift values, and then the artificial neural network, it will map it to something, another input that will make sure that we'll actually get what we want. So basically it will bridge this gap for us. So and it's quite important because there are lots of different patterns and unpredictabilities involved. Unpredictability for us, for humans, which are repeatable patterns, and an artificial neural network system or any other machine learning system can take advantage of. So in this case, we managed to take care of this problem, and this is the results. I don't want to go into detail. It's the lookup table for mapping phase attenuation pairs to the corrected digital command. If we use a table instead of the artificial neural network, it provides us with somehow a better accuracy, but it takes a lot of space in the small elements that we are generating. The elements that we are talking about are very small. It can fit in the palm of your hand, and it's quite packed with lots of different hardwares. So if we can reduce the size of the memory that is required to perform this task, it's much better. So for the phase shifters that we have in our system right now is 5-bit phase shifter. The table is 8 kilobytes. Requires 8 kilobytes of storage. Artificial neural network needs 1.46. And then if it becomes 8-bit phase shifter, the reduction or compression of data is much higher, 512 kilobytes comparing to 6 kilobytes. And then for 16-bit phase shifter, it's 32 gigabytes versus 48 kilobytes, which is amazing. And that's the beauty of AI systems that can help us to bridge these gaps. The next part, how much time do I have? I think good. Yeah. The next part is the actual tracking system. So I said that here we have these historical readings, and based on that, we'll find the location of the satellite. It's not an easy task, and always there are errors involved, there are statistical problems involved, the fitness functions that we have to use are different, and it's a quite complicated task. So what we did is also use another artificial neural network here. So basically, the system needs to predict two angles. The first one is theta, which is the angle between the vector of looking direct to the satellite and the perpendicular vector to the north, and the other one is phi, which is basically your direction when you're looking to the horizon. And these two angles are the two angles that are the output of the system. So these are the things that we have. We have this many readings, and this is the surface, basically the 3D surface that the system generates based on that and gives you the result, one phi and one theta. That is the location of your location right now. And again, let me just talk about the AI system and come back to it. Again, we use artificial neural networks. I'll talk about the details of this one a little bit more. We provide the historical satellite direction readings. We train the artificial neural network to detect the correct orientation based on that, and then get the high accuracy readings. So this is a representation of that system. We have 200 input nodes, which is basically 100 pair of satellite locations that we have had for the past 1 second, 2 seconds, let's say. And then we have 2 hidden layers. The first one is 100 nodes, and the second one is 50 nodes. And the output is just 2 angles, phi and theta. And after training this system for 50,000 times, the accuracy is quite acceptable, not acceptable, it's quite good. And it actually can be used in our system for real-time finding of the satellite. So comparing to the previous system, the system was quite, optimization was quite time-consuming, and the fitness function is not consistent. Sometimes it's two-dimensional, polynomial of 2nd degree, sometimes polynomial of 3rd degree, sometimes it's not polynomial at all. So there are lots of mathematical complications involved, and the robustness is not as good as the artificial neural network, because it depends on the experience. It learns a lot, and that learning pays off during the operation of the system, and it becomes quite robust. Now I will give the podium to Naime for the digital antenna design.
Hello, everybody. Milad, I have to ask you to change the slides after each slide, please. Okay, designing, this is another application of intelligent systems for antenna designs. Designing an antenna is kind of, if anybody who is kind of involved in that knows that it is a very tedious and time-consuming process, because it's we have many constraints and specifications that should be satisfied at the same time, and so there are many trade-offs between them. But using a machine learning can save the time of the designers and make this process easier. Would you please go to the next slide, Milad? Okay, so in a kind of conventional way is that we kind of, with having the specifications, we go with the initial design or initial guess, and kind of do some simulations with for example, HFSS, simulators, FECOs, things, and then we kind of compare the results with the specifications. It is not what we want. We have to modify the designs and then go again. And so this is not a kind of, it's a kind of very iterative process, and it's very time inefficient. But if we are going to use the machine learning instead of that, we kind of, the first thing that we should do is just building a parametric model, and then we do studies on this parametric model to do some kind of design some tests, and we find that which parameter has more impact on the final solution, or for example, on the directivity or on the polarization or other parameters of the system. And also we are kind of generating data to kind of training our machine learning. This after we do this data collection, which is taking it is also time consuming, but not as the previous one, the previous model. But then after that, when we kind of use this data to train the machine, optimizing the system would be very fast, and and in general it saves the time. Kind of, and also if we kind of we can reuse these trained model for similar structures, but maybe for different specifications, but with a similar feature. So would you please go to the next slide? So the first thing is that kind of we should build a parametric model. So here kind of we do a shape optimization on a curved wire antenna, and I am kind of describing how we parameterize this the complex feature of the antenna. So we know that in mathematics that each point on the curve can be determined by two polar spherical angles of each of the unit tangent vector at each point. So we kind of divide the curve into different segments, and for each segment we can define the alpha and beta angles. Would you please go to the next slide? So, by the shape of the overall the antenna can be defined by the alpha and beta functions versus the total length of the wire. And so another step is that, okay, we kind of should discretize this function, and then you can see that we just define the functions at some discrete points. So would you please click? So here I just show you that how by changing only one of these parameters, the shape of the antenna is changing. The left picture is showing the alpha S function, and the right one, yes, is showing the actual shape of the our wire when we are changing just one of the parameters. So would you please go to the next slide? So our optimization parameters are now reduced to alpha 1, alpha 2 values, the distance between these points, and the beta values, and this. So we kind of with these optimization parameters we start our algorithm. Would you please go to the next slide? So one of the examples applications that we required to design an antenna with lots of restricted specifications is for calibration of our phase array antenna. So we have a very big scale phase array antenna, and we need a kind of probe antenna to get a feedback and use that feedback to calibrate the system when for in situ applications, for onboard applications. So there are lots of specifications that I have listed here. It should be a small, not to block this signal coming from the antenna. It's we should put the antenna very close to the phase our antenna to keep the whole structure low profile. So while the antenna is very close, while our sensing probe antenna is very close to our structure, it should be able to see all the antennas at the corners of the and at the edge of the phase array antenna. So it should be wide, have a wide beamwidth to see all the elements on the array. It should cover the whole frequency range, so it should be wideband. It's we have a circular polarization, so it should have a good polarization, good large 3 dB axial ratio. So these are many specifications that should be satisfied for at the same time for antenna. So the solution to do that is to do kind of a very extensive shape optimization for this antenna. Would you please go to the next slide? So this is an example of a shape optimized wire antenna, which is very small, and also it has a very large beam width, and very good polarization behavior. Has a 3 dB axial ratio of 245, which is kind of very good. And I think let's stop at this point because I think we are past our time, but let's skip this part. Okay.
Okay. All right. Well, thank you, Neva, and thank you, Milad. That was for your presentation. That's very nice. So I guess we'll open the floor to questions. We do have a minute or two for questions. One question that's come up is, depending on the application, you're using training sets. And do you see the training set for the neural network as something you would do exclusively up front, and then when you have an antenna, let's say as a product, it would be locked in, or do you see the training ongoing as part of the learning process in service?
Actually,
is it a question from me about the designing the antenna?
I'll let you guys decide.
Oh, okay. If it is the part that is related to the design of the antenna, no, it's not. We kind of to think is we are kind of using simulators. Yeah, no, I agree with you on that. But maybe Milad, in your application you described.
Yeah, in the application that I have right now it's stationary. So with data that we use for training, it's just the previous set of data, and the artificial neural network is designed, and that's it. But I think you need to do a update and recalibrating of the system, and every once in a while, it would be actually ideal if we can retrain the system while it's doing its normal operation. So, but right now it's just offline. So we generate the system and use it afterwards. Yeah, thanks for the question.
Okay, and then another question is from a functionality and again industrial readiness or consumer readiness perhaps. Where is this at? I mean, you've got these mobile arrays that you're proposing here. Are they prime time? Are they in service yet, or how far out is it? I'm just curious.
It's a part of the CCOM satellite system, so they're actually supporting this project, and we're moving forward. I'm not sure if it's commercialized yet, but it's the last stage of research. So we are far past the proof of concept and the pilot systems, and it's been getting closer to an actual product. I think next 5 year, maybe, name it. Can you? I think in the next 5 year we will see the first products.
Okay, no, that's great. Thank you very much. Are we seeing any more questions, guys, coming down? I'm not seeing any in the chat right now. I just wanted to double check before we moved on.
Nope, there's no other questions in the chat.
Great. Well, that's fine.
Thank you so much.